Welcome back to our introductory Fortran tutorial. We're just at the end of the tutorial almost. I'm just going to take you through just the final section on reading and writing to output files. And this enables you to interface Fortran with many other languages. So you can write out the results of a calculation to a file, read them in from a file that's been spat out by another language, read your file into Python, plot your file with GNU-plot or whatever other tool that you would want to use. I'm now going to take you through just a couple of the exercises at the end of the tutorial. So just as a reminder, this is our Introduction to Modern Fortran tutorial. I'm Daniel Price. I'm an Associate Professor at Monash University in Melbourne, Australia. And this is part 4 of our tutorial. So we're nearly at the end now. So again, just a couple of things that we've learned so far is always to put the main functionality in a module. And you can see already I've got lazy at the end of this tutorial and put some of my stuff just directly in a program. Whereas what I've been teaching you so far through this tutorial is really to make your program as small as possible and to put all of your functionality into a module. So I'm going to continue with that practice. I'm just going to close actually some of the modules that we're not going to use anymore. So just simply keep my main program, my make file, and the module we're going to be working on. So I'm going to just make a new module now called io.f90. I'm going to open it in my editor here, which is called Atom. But any Unix text editor will do the job. In fact, some of the text editors have advantages for programming. Emacs has some nice features. Atom, you can see, one of the most basic things you would want in a text editor is that it does what you call syntax highlighting. So it highlights what are Fortran keywords and it highlights what my names are. And when I type something like implicit none, it knows that that's a Fortran command, and so it highlights that in blue. And in Atom, that's just done by installing one of the packages. So if you look in your settings on Atom, then there's various various packages. And if you simply search for Fortran in the packages, you can see I've installed the language Fortran package, which is giving me the syntax highlighting. So it doesn't really matter which text editor you use, but some have very nice features, and a lot of them are built for with programming in mind. All right, so I'm going to make a module called IO, and we're going to make two subroutines. So I'm going to make a subroutine called write to file. I'm going to make a subroutine called read from file. Read from file. Sorry, that should be the end subroutine. Write to file. I'm going to make a subroutine called read from file. Why don't we just call it read file? Or do write file and read file. And end subroutine read file. Okay, so the purpose of these should be clear. So I'm going to make some comments. So this is a module to handle input, output to and from data files. Okay, but I'm just going to show you some of the simple Fortran syntax for this. So let's put a comment at the top of each of our subroutines. So this is a subroutine to write a data file. And the purpose of this subroutine is to read a data file. So the most basic comment you should add is basically to state what the purpose of the subroutine is. So we've got implicit none. So the other thing we should do by default at the top of modules, I'll just make this a little bit bigger so you can read it, is make everything private by default and just specify that the only public information is what we want the file to be. Now I'm going to take a little bit of a variation on what's in the tutorial sheet. So for example, the arguments we're going to need a file name, and we're going to need the data. So in this case, I'm just going to send two arrays, and I'm going to write a simple kind of 2-column ASCII file. So I'm just going to write a text file essentially, and these X and Y are arrays, and they're going to have a certain length. All right, so let's do that. So when we say, so these are going to be real variables, the x and y. Now, so x and y like that would be variables which are not arrays. Now, I want them to be arrays, but I actually don't know how long they're going to be. So I'm going to declare them as what you call automatic arrays in Fortran. So that means the length is determined by the whatever called this routine. It's the length of the array that it was called with. Now, those have to have intent in because they're an input to this subroutine. Although they're going to be written out to an output file, they're an input to the subroutine. In other words, this subroutine is not going to change the value of anything in the x and y arrays. All right, and the second thing is the file name. So we haven't used a variable like this, but we're going to use the character variable. So with a character variable, you need to give a length of the string. So it's just a string. It's just a number of ASCII characters. So if we had a string length 20, we would expect a file name of length 20. But what you can do, again, with characters, you can set the length to be automatic. So let's have the length of the string to be set by whatever length of string I pass into this subroutine. Okay, so like all good programs, I'm not going to try and do too much. I'm just going to simply print the value of the file name, and then I'm going to print x equals, and I'm going to print y equals y, and x equals x. Okay, so my read file routine is just doesn't do anything at the moment, and my write file routine has got some structure to it. So let's, now really, I mean, I originally called this program maths.f90, but let's just call this, so probably a good name for the main routine, which would be the default in C, would be main.f90. So I'm going to just change the name of my program to be called main. I'm going to match the name of my program with the name of the text file. And all that I have to do then is change the name in my make file here, so main.f90. And I'm going to add my module io.f90 and my main.o, depends on area, precision arrays.o, and io.o as well. All right, so let's type make. And then we have our program is now called main instead of maths. Well, not quite. It's because we didn't change the name there. So now my program is called main. All right. So I'm going to type make clean and make, and we should have a program called main that does what we want it to do. All right, so this does actually the same things it did before because I haven't changed my program. So I want to now use my IO module. I'm going to call write file. So now I need to figure out the syntax of my write file routine. So I'm going to use the only statement, so write file, to say that's the only thing I want to call. And I'm going to call this file name results.out. And I need to send it to arrays, x and y. So I'm going to just declare them here as real arrays, x of length, let's call it 3, let's call it 4 actually, and y of length 4. I'm going to say x equals 1 and y equals 26. So if you remember how we set arrays, this is equivalent to putting the colon there. So that means all 4 values of the x array are going to be equal to 1, and all 4 values of the y array are going to be equal to 26. All right, so these arrays are of length 4. I'm going to write my file with this file name, and I'm going to send it the x array and the y array, and hopefully what this program is going to do is write it out to a file. All right, so let's type make, and we run main now instead of maths. And what happens is I'm just going to get some output to the screen, first of all. But you can see that I've received this variable, which is a string called results.out. Sorry, let's have a look in this routine. So I've got this variable called results.out, and I've just printed it. That's my file name. And I've got these x and y. I have exactly what I sent into this routine. Now, You've come across in the previous tutorial the write statement. So equivalent exactly is the same as print, would just be to use the write statement, write star comma star. So I'm going to change this to use the write statement instead of the print statement. Now the write statement takes 2 arguments. Now the second argument is just the same as the one in the print statement, so that's the format string. So if we wanted to format these in a particular way, we would specify the format string. For example, we could use extended scientific notation, 12 characters in total with 6 digits after the decimal place, so extended scientific notation 12.6 again. I'm going to drop the string now. And actually, I'm going to write these numbers on the same line because that's the kind of file that I want. So I want a space between my numbers, extended scientific 12.6. All right, so this is just the same as a print statement, except that I'm saying explicitly how I would like these numbers to be formatted when I write them. Okay, so let's do that. Syntax error, that's because this all needs to be in quotes and brackets. So that is now my format string. So that's just a string like any other string variable in Fortran. So I could make a character variable. So for example, I could make a character variable, character length equals 20, format string, and I could say format string equals the stuff in quotes. So I could simply say, replace that with that, and I could put format string there. And that would be equivalent. So it's just a string variable, but you don't, using a variable here seems a little bit unnecessary because we only specify this format string once. Okay, but this is essentially now, we're currently writing this to the screen, but you're going to see in a minute what this other argument is for. Okay, so we can run our main program, and we can see we get 2 columns of output to the screen. We get, now this is a bit tricky because this is not what I intended. What I really would like is, so I've got x, 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 y, 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 whereas what I really wanted was the first value of x, the first value of y. So what I want is a loop, do I equals 1 to the size of x, or actually I don't actually know that they've got the same size, so I really should do the minimum of the size of x and the size of y, and print out the value of x of I and y of I. All right, so let's do that again. So again, you notice this cycle of just do a small amount, test, just do a small amount again. So here I've got an error. I've got symbol I has no implicit type. That's on line 16. So I've used this symbol I, but I haven't given it a type. That just means I need to declare it as an integer variable. All right, so let's try that again. Type make, there's no errors. And let's run the code again. So again, we get this string printed to the screen, but now I get x, 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 which is x1, x2, x3, x4, and I get this y string, which is 26, 26, 26, and 26. Okay, so let's just maybe make our arrays a bit more interesting. So let's make our x to be 1, 2, 3, and 4. And why don't we just simply say y equals x squared. Now you can do this with arrays in Fortran. So the values of y should just be the values of x squared. All right, so let's do this again. Print it to the screen. You see 1, 2, 3, 4, 1, 4, 9, 16. So that's the 16 because it's 1.6 by 10 to the power of 1. That's what the e plus 1 means. All right, so the only thing we need to do now is to actually, instead of writing this to the screen, which is the default unit here. So this argument to the right function is called the logical unit number. Now writing to unit number 6 is exactly the same as writing to the screen. So we type make, and we type main, and we get exactly the same output we did before. But we could now change this number. So if you are really, really lazy, the only thing you have to do is change that number. So you can write to unit 1, for example, instead of unit 6. Now unit 1 is not the screen. So if I type make, and I run main again, I get no output on the screen apart from the print statement. But when I look in my directory, I'm going to make clean so that you can see it a bit more clearly. There is a file called fort.1. And if I look in this file, more fort.1, then it exactly has the stuff that used to go to the screen is now in a file. Now, calling my file fort.1 is not particularly good practice. But if you really want to be lazy, yeah, you could do it that way. Instead, what I want to do is I want to open a file. So you want a file on unit 1, and I want to specify the file name. File equals file name. Now, it's good practice. So the other arguments are optional. So file equals file name, which is just a string. And I want to say something like status equals, now the status can be either old, new, or replace. So I'm going to show you what happens if I do status equals new. So which is that I'm going to make a new file. I'm going to close file 1. And maybe it's a good practice here to just do something like, now instead of using the star, I'm going to use a format string here, so ASCII. I'm going to say I'm going to writing to, and then I'm going to append my strings together. I'm going to writing to file name. Now it's helpful to trim the white space. There's a Fortran function called trim, which trims the white space. So I'm going to writing to trim file name. All right, so my program should just tell me when I run it, so /main, writing to results.out. So that's what I wanted, but now I should have a file called results.out. I'm going to delete and make clean so you can just see what we're doing. And you can see I do indeed have a file called results.out, the contents of which is precisely what I used to be putting out to the screen. So that's the basics of how you write to a file. But what happens if I run my program again? Now the difference is that results.out already exists. So if I try to play the same game again, I get Fortran runtime error, cannot open file results.out, file exists. So it's at line 17 of file io.f90, unit equals 1, and I don't really get this backtrace about where that was in my code. So if this was in a piece of much more complicated code, you might like to know, well, you do get a line number here about where the error occurred, but you might like to see where that subroutine was called from. So you can do that, for example, with some debugging flags, which we haven't covered yet. But so some of the debugging flags are -f check equals all, and you can have -f backtrace, should give us this backtrace. So now if we make clean and make, then we do not get a backtrace. So instead we'd have to run this in a debugger. So for example, LLDB, and if I run /main, run, oh, there, /main, and run, that still doesn't help me. Probably because I don't have debugging symbols, so I sometimes need the -G. Let's just try that one more time. Make clean, make, and then LLDB./main. Still doesn't give me a backtrace. Never mind. All right. But we get the idea. So the error is on line 17 of file io.f90. And the problem with the error is that this file already exists. So the status equals new means the file cannot already exist. It must be a brand new file and it shouldn't overwrite anything that's there. Old means the file must already exist. So not existing already would be an error. And the final status that we want is status equals replace. And there's another keyword here which is helpful, which is the action. So we want the action to be write, and we want the status to be replace and the action to be write. And those things are just helpful because you're giving the compiler a bit more information. So for example, if you specify that action is write, then you're not allowed to do a read statement. You're not allowed to read from that file. You're only allowed to write to it. All right, so let's type /main again. and we write to results.out, and now we don't get an error because it's an acceptable with the status equals replace. It's acceptable to simply replace the file with a new version. All right, and if you look at the timestamp on that file, for example, so ls-l, you can see it's made at exactly now. All right. So the final little nugget here that I'm going to give you is this unit number. So we've just chosen an arbitrary number like 1. But you might think, well, I don't really know which unit to choose. And what you want to do is just simply choose a unit that's not being used by some other subroutine. So the right way to do that is to declare an integer variable. Let's call it ru. And let's call it unit equals ru. But instead of unit equals, you can just use the Fortran 2008 keyword new unit equals, and you write ru and you close ru. So it uses this integer variable ru, and it just selects for us a unit which is not being used. And we could, for example, let's just move this print statement down a bit further on unit ru, and we can see which unit it's going to be using, but it's going to select the unit for us. Now, because this is a string and this is an integer, I need to add the format code i2 here. Well, let's use i3, which is an integer printout with 3 digits. Okay, so let's type make, and run our program called main. Actually, it said unit -10 apparently. So it's probably a special unit that's being used internal to Fortran. So it's really using unit 10, but I guess it's an internally tracked thing that you don't really need to worry about. But so the unit identifier is given to you by Fortran. All right, so that's the best way to kind of write a file. And then if we simply want to do the opposite, then we can just read the file. So it would be the same file name, x and y. Now, the same kind of structures to our subroutine, character. Now, what I didn't do here is specify the intent. So the file name should definitely be an input to this routine, character intent in. But my arrays are now going to be intent out. That is, this routine is going to read them, and it's going to send them back out of this subroutine. All right, so the basic gist of this is that I should just do the opposite of the other subroutine. All right, so let's do the same thing again. So we're going to open new unit equals ru. So we've got an integer variable, ru, and we're going to use the I as well. File equals file name, status. Now the status should be old here because we want the file name to exist. So it's going to be an error if the file that we're trying to read from does not exist. And the action should be to read instead of write. Okay, so then it's the same thing again. Do I equals 1 to size, the minimum of the size of x. Well, let's just do 1 to the size of x. Undo and close the unit. Okay, so it's just the same as the write statement, except we do a read instead. So read ru. And again, you can specify the format that you want to read, but usually when you're reading, it's best to give the just the list directed read, and you read x of I and y of I. All right, so that's how we read a file. So it's just the opposite. So you just open, read, and close. Okay, so we're going to do that from the main routine now. So I'm going to just do a little demonstration first. So let's then override the value of x and y with zeros. So this is a little unit test of our read and write files routine. So let's write x equals x and then print y equals y. And we should just get zeros instead of, so we're going to write these actual values to the file. We're going to reset them to 0. And then in a minute, I'm going to read the file back again. and we're going to hopefully recover the values we gave this array in the first place. All right, so let's do that. Ooh, but we've got symbol I has no implicit type, so that's line 32 of the file io.f90. So let's go to line 32. So we haven't specified integer I as an integer variable because we declared implicit none at the top of this routine. And I'm going to add one more line to this as well. I'm going to get rid of this unit stuff because we don't care what the unit number is. I'm going to just put in a print statement that says print reading from the name of the file. Okay, so let's make clean and make and run our main program again. All right, so now we can see that we've got this file. Now, if you really want to be sure that this file was printed out by the code, let's delete it and then run it again. And then we can see that results.out exists, and it contains indeed the values that we wrote to the file. But x and y are now 0. So what my hope is going to be that when we try this, putting in this read file routine, we're going to get back the values that we had to begin with. All right, so let's try and compile that. Okay, so we've got this funny error now, which is undefined symbols for architecture, blah, blah, blah. Read file reference from main in main.o. LD return 1 exit status. Now, what does this mean? Well, it simply means that it doesn't know how to find the routine called read file. And that's because we haven't put it into this use statement at the top of the program. So we should do it like this. So we need to import the routine definition from the module in order to be able to call it. And after that, everything should work. So we type make again, there's no errors. This undefined symbols error has gone away, and we should be able to run our code. All right, and indeed, you see that what we get back, instead of zeros, we now get back the original values in the file. So that's the basics of reading and writing from a file in Fortran. Now these files are simply text files like everything else. So for example, I can open my results.out in my editor. But let me just show you a couple of pitfalls, for example. So what if I add another line to this file? So my text editor, I add another line, 26, and then I try and run my actually, what if I take away a line? So what if I delete a line? So I've only got 3 lines, but I'm expecting 4 quantities when I read it back in. So let's just run the program again. And I'm going to comment out my write statement now. So I'm just going to do the read, but not do the write. So let's type make. And you can see Fortran runtime error, end of file, at line 34 of io.f90. So it's trying to read this file, but it didn't find enough numbers in the file, so it encountered an error. So the one last little thing I'm going to show you is that it's not very nice that Fortran gives you these runtime errors when you know that such an error is possible. So if you want to sort of silence the error, we can simply declare an integer variable called iError, and we can do iostat equals iError, and we can simply print for ourselves if, so what we might do, for example, is just read as many numbers as there are there. So do while iError equals 0. So we should make sure we set the iError equals 0. And do while iError equals 0, we'll just read all of the files that are, the lines that are in that file. Let's do I equals I plus 1. Every line we read, I equals 0. And that will just read whatever numbers are in that file. All right, so far so good. Now this is a little bit dangerous, but you're going to see what happens in a minute. I'm going to just take off this -f check all because I want to show you in a minute what that's going to do. All right, so let's type make clean, make, and /main. Okay, so far so good. We simply, the program actually didn't read everything because you can see the last digit in the x and the y is just 0. So actually this is a bit of a problem because we actually didn't know, or we did set it here, but what if we were simply supposed to read this file to set the values? Now you still get a 0 here, but it's certainly not guaranteed that you're going to get a 0, it's just undefined. So this is a quite common error, and it's called using a variable undefined. And then just notice that it hasn't been picked up by any of our flags here, so my compiler flags all seem to work just fine. So it's a tricky one to pick up, but you should be aware of it. So one simple way you could fix it would be to use -f init real nan. So that means initialize all real numbers to not a number, and then when you run the code again, -f init real equals nan. And then when I run my code again, you can see that I actually get a nan instead of a 0. So by initializing all reals by default to something stupid, you can actually help to track down where you might have used a number uninitialized. So other compilers have better features for detecting this kind of error. But I want to show you one more kind of error you might result as well. So let's imagine that our results.out had too many entries in it. So let's imagine that it had 6 entries instead of 4. So I'm going to run this again. And everything worked. Why did that work? Good question. Because my x only has the size of 4. But my results file had a lot of numbers in it. So this really shouldn't have worked. So let's just put some different numbers here. 12, 13. Make clean, make. Okay, and this seemed to work quite happily. Maybe let's just put a little printout. So we'll just print out what number we got up to here, just to see where we got up to. So let's type make and type main. So we got 1, 2, 3, 4, 5, 6, 7. But you notice in my subroutine here, my reals have only actually got size 4. So it's a remarkable thing, but I've actually done something that's extremely undefined here, which is I've tripped off the end of my array bounds. Now this is very dangerous again, but again, it's very easy to check. So I use the flag called fcheck equals all. Now in general, you should not leave these kind of flags on when you're sure that your code is working, but these kind of flags in the compiler are really good for debugging. So if you want to make sure that your code is correctly working, I would recommend leaving them there. But now if I run my code again, I get an error. And it says line 38 of file, index 5 of dimension 1 of array x is above the upper bound of 4. Right, so this fcheck all in particular is a very valuable check, which checks that I'm not tripping over the array bounds of my arrays. Now the behavior once you do that is undefined. In this case it seemed to function perfectly well, but in general you'll get a segmentation fault when you do that. Okay, so the way to pick up those kind of errors is by -fcheck equals all. But again, the sort of lesson here is that you want the compiler to do the job for you. So that's kind of covering the basics. We're getting on to more advanced topics now, but you're hopefully getting the hang of how you kind of write code in Fortran by now. And that's the basics of how you read and write your output to a file. So we can probably go ahead with a more physics-based tutorial about how you might write some kind of physics code. And I'd encourage you to just go over some of the Fortran primer or some of the more basic tutorials that you can find on my website. To learn some of the syntax which you need to be able to write code efficiently. Thank you.